Today, we're jumping into a scientific showdown that honestly feels like it's pulled straight from a sci-fi novel. But this is a very real debate happening right now in the world of astronomy. So, get this. What if photographic plates, a century old from long before the space race, actually hold evidence of unknown objects orbiting our planet? That's the incredible question that sparked the entire controversy we're about to unpack. It all kicked off with a project called VASCO. Now, their original mission was to scan old sky survey plates looking for stars that had, well, vanished. But instead, they stumbled onto something completely different. Thousands and thousands of mysterious, fleeting flashes of light. Astronomers call these transients, and these specific ones from the 1950s just didn't seem to line up with anything they knew. And that's when things got really weird. The researchers noticed a pattern. There was a distinct lack of these flashes right in the patch of sky where the Earth's shadows should be. Our planet's eclipse. This was a huge clue. It strongly suggested whatever was causing these flashes was close by, reflecting sunlight and then disappearing as it passed into Earth's shadow. And we're not talking about a subtle hint here. In science, you use a measure called sigma to gauge how likely something is just a random fluke. 5 sigma is usually considered the gold standard for a discovery. Well, this Earth shadow deficit clocked in at a jaw-dropping 7.6 sigma. That is a massive signal, the kind of thing that makes scientists everywhere stop what they're doing and pay very close attention. As if that wasn't enough, the rabbit hole went deeper. The team found some other really bizarre correlations. The flashes seemed to spike during periods of atmospheric nuclear weapons testing, and they even found cases where multiple flashes appeared close together on the same plate, which is super hard to explain away as just random emulsion defects. But you know how it goes in science. Extraordinary claims demand extraordinary proof. So it wasn't long before another team of researchers, led by a scientist named Waters, published a detailed critique that challenged pretty much every part of the original findings. Okay, so the whole argument basically boils down to these 4 main beefs. The critique said, hey, we don't see that Earth shadow effect in our data. They argued the nuclear test correlation was just a coincidence. They claimed the flashes were probably just smudges and defects on the old plates. And finally, they said the whole statistical method was wrong to begin with. Well, the original team, led by Beatrice Villarreal, they weren't taking this lying down. They fired back with a comprehensive rebuttal. And their main point was that the critique completely misunderstood the whole point of their analysis, especially when you're dealing with messy, noisy data. They explained that their work relied on ensemble-level inference. What that means is they weren't trying to prove that every single one of the thousands of flashes was a real object. Instead, they were looking for patterns in the entire collection of flashes. Think of it this way. You don't need to check every grain of sand on a beach to know which way the tide is going. You look at the overall pattern. And they made this killer point to illustrate what they meant. They said, if you demanded a perfectly clean dataset with 0 errors, you'd have to shut down massive projects like the Large Hadron Collider at CERN. That's the place that found the Higgs boson by finding a tiny, tiny signal buried under a mountain of data noise. Okay, so that begs the question, right? If this Earth shadow effect was so strong, why did the other team completely miss it? Well, the rebuttal says it comes down to a classic problem in statistics, a lack of power. I mean, just look at these numbers. It's a tale of 2 completely different datasets. The original study had a huge sample of about 107,000 transients. The critique, on the other hand, used the super filtered down set with less than 5,000. That's a staggering 95% reduction. When you shrink your sample size that much, your ability to detect a real effect just plummets. And it's not just a hunch, they actually ran the numbers. They showed that even if their 7.6 sigma discovery was 100% real, cutting the data down that much would mathematically reduce the signal to an insignificant 1.6 sigma. So in other words, the critique sample was just too small to have ever seen the effect in the first place. But they didn't just stop at your sample size is too small. They went even further and raised a huge question about the critique's fundamental calculations. They basically asked, hey, did you guys even do the math right? All right, this looks a little technical, I know, but stick with me, because it's a huge deal. When you try to map a 3D sphere, like the sky, onto a 2D photo, you have to apply a geometric correction. It's like trying to flatten an orange peel without stretching and distorting the continents. The image on the left shows the data with that crucial correction. The one on the right, which looks a lot like the plot from the critique, shows what happens if you forget it. If that correction was missed, it would throw off the time and date for every single flash, making the entire analysis flawed. Let's switch gears back to those other strange correlations. The critique said the link to nuclear tests was just a coincidence based on when astronomers happened to be observing. So the rebuttal team said, okay, let's rerun the numbers your way. So they used the stricter method the critique suggested, looking only at nights they knew for sure had observations, and look what happened. The correlation didn't vanish. It actually got stronger. On nights with no nuke test, about 73% of them had a transient. But on nights that fell within a nuclear testing window, that number jumped to over 84%. The bottom line? This result was statistically significant. The p-value, which is basically the probability of this happening by random chance, was less than 5%. That suggests the link between these flashes and nuclear testing is very likely more than just a coincidence. So, after all that back and forth, where do we stand in this incredible scientific debate? Well, the rebuttal concludes that their original findings, the Earth shadow deficit, the historical correlations, they all hold up. They haven't been disproven. And they wrapped up their argument with this really powerful idea. They're saying, look, of course some of these flashes are just dust and scratches, but if you get so obsessed with those individual flaws, you risk completely missing the forest for the trees. And in this case, the forest is a huge, clear, large-scale signal that seems to be hiding in the data. And honestly, this is exactly how science is supposed to work, this rigorous back and forth, this challenging of ideas. The case isn't closed at all. If anything, it's just getting started. The mysterious flashes are still there, unexplained, leaving us with this incredible question. What in the world are they?